So we are doing a difference quotient problem. Evaluate. So what are we evaluating? We're evaluating this thing. F of A plus H minus F of A all over H. That's the thing. Okay. So if you know how to do that, then begin. If you don't, there's like several levels of like where you may be confused. The first level is, what do I do with that? What do I do with that thing? Can anyone tell me what I do with that thing? 1 over A plus H. And it's very precise. It has to be 1 over A plus H. Precisely that. Nothing else. It's not this. A lot of folks will write that, and that's super wrong. Okay, there we go. Then we have this subtraction sign. We all know what to do with that. We subtract. And then we get this part. So let me ask someone behind this way, where did this 1 over A come from? That came from, everyone says, there, right? All right. So now we have this division bar. You should know where that comes from, and then the H. Okay. Now we get to this part that's like, we have to be a bit creative, because you may not know what to do here, but I claim if you're like courageous enough to just start to try things, you might succeed. Any ideas? Beautiful. Now that trick works for all of these types of difference quotients that are fractions, that are rational expressions. So here we go. Common denominator looks like this. There's like a green piece and what is that? Orange piece. The green guy needs an 8 over A. So we need to basically think about this. We need to think, I'm going to multiply this by A over A. That's what you have to think. And then whatever this color is needs an A plus H over A plus H. But put things in parentheses so that you don't screw up the distribution. So downstairs, the denominator is exactly A on A plus H. And upstairs, you have an A coming from this first distribution, and then you have a subtract A plus H on the last one. And I'm going to make a mistake, and you tell me where it occurs. Should be a negative H. So this is the pitfall that's going to catch 60% of the problems people do by going from sort of the left side to the right without realizing that you're actually subtracting off an entire A plus H. Boom, that's all there is to it. So what that means then is that you simply on the upstairs you have negative A minus H. Downstairs you've got an A on A plus H all over H. The A's cancel. So then you're left with a negative H over an A on A plus H over H. And then it's up to you, well, once I train you, to know what to deal with that, how to deal with that. And the way is this. You simply think about this first. There's a top fraction, and it's being divided by a thing. Dividing by a thing is the same as multiplying by the inverse of that thing. So just scratch out that thing and multiply by 1 over H. That's all there is to it. Now the H's cancel. These two H's cancel, and you're left with -1 up top over a on a plus h. And then put a little, box around that or something, circle. Because that's it, we're done. What do you think? Can you do that? Let's do one more. Yes, ma'am. Yes, sir.
Just double checking. They can leave the Google call, right? Or
yeah. Totally.
Okay.
Totally. I'll get it posted later when I get my Wi-Fi back up and running. Yes.
What's like the overall definition of a difference quotient?
It looks like this. Oh, come on. Well, I don't know where that went. Let's see if we can do. Okay, the overall definition. So we're at a new page. The definition looks like this. Quotient looks like this. F of, often you'll see an X or an A. It doesn't really matter what letter that is. It's as long as it's an F of a variable plus H, subtract F of that same variable over A plus H minus A. But this is, so what's important, right, is that you've got this A plus H fed into the F upstairs, and downstairs it's just the A plus H. And then you're subtracting F of A at the upstairs, and downstairs there's that A. So that's the difference quotient. So, but most often we do the math here and cancel these A's, and we get to this thing. So that little piece, this is, so that piece, this difference quotient, it does a lot of different things. Because it is a piece of the definition of the derivative, it does a lot. It can calculate average velocity. On some of your web work problems, you're going to get an average velocity question. And this is essentially the answer. This is essentially a slope formula. This is a slope formula where x1 equals a plus h, and x2 equals to a, and y equals to f of, or y1 equals to f of x plus h, and y2 is f of, or I guess I should say, let's do a plus h, and x2 is just a, here we go, sorry, and this is a plus h and a. So it really is just a slope formula for a particular function. Okay, so that's probably a good, I said I wanted to do one more difference quotient problem, so let's do that now. Looks like this. Let's do a good old-fashioned square rooter. Now, by the end of the first exam, you'll have to know what this difference quotient is, and so, but since it's early, I'm going to tell you, I'm going to write it down again. F of a plus h. So you're going to have to produce this formula that I'm writing now, but from scratch. So evaluate this. Yes.
This is, I immediately have raised my hand. This is probably a dumb question, but will there ever be an instance where it's f of a plus h plus f of a?
No, and the reason is, think about that slope formula. What's the slope between 2 points? It's always you take your x1 comma y1, and you take your x2 comma y2. The slope is always and forever the y2 minus y1. That subtraction here is this subtraction.
Okay. Thank you.
And likewise, the x2 minus x1. So there's all we're doing is just changing labels. It's just label changing. Still, this is definitely, you should think about as a slope. Okay, so you guys try this, get started. You're going to hit a roadblock, and I'll help you once you get the roadblock. Anybody move past the kind of this first stage? Yeah, those things that your math teacher in your previous life had trained you to do come handy here. Rationalizing the numerator is exactly what one needs. So what the phrase is this. It's called a radical or conjugate radical. So conjugate meaning, what does that mean? Well, it means it's effectively the same thing, but the sign, one sign has been changed. That's essentially what we mean by a conjugate. It's essentially the same thing, except the sign has been changed. So these two, this green thing and this, I keep thinking spacing on the color there. We're going to call that orange thing. They're conjugates. They're essentially the same except that one sign. Yes?
Are you saying sign or side?
S-I-G-N.
Okay.
That negative's changed to a positive. Now, you've got to, so this first, and so what we're doing, right? We're multiplying by 1. We're not changing the problem. This is like this bit of this opportunity for mathematicians to be creative. We're doing nothing and something at the same time. We're doing nothing because we're multiplying by 1. That does jack squat to the expression. It doesn't change it at all because you're multiplying by 1. You can do that. But we are changing its form because when you multiply these two together, you're essentially doing this. You're essentially multiplying an a plus h to a 1/2 times an a plus h to a 1/2, and you're getting an a plus h. So this equals, this first part will be a plus h. And this next part, let's do in our heads. Check it out. I'm going to take this guy and multiply it by radical a, but I get a positive sign. Okay, that's over here. Then I take this thing and I multiply it by that thing. It's the same deal, it's just the order has switched and it has a negative. So they cancel, so I don't even write it. Then I get the last bit of multiplication and I subtract a single a because the radical a times radical a is just a. So that cleans it up nicely upstairs. Downstairs I have an h on some stuff. Downstairs this stuff just keeps staying stuff. There's nothing magical that's going to happen to it. It just stays what it is. It's sort of like you push the complexity downstairs. Yes?
So, on top, are we foiling?
Yeah, yeah. First outer, inner, last. Total foil, exactly.
Or
You got it. That's a good question. I should have said that ahead of time. Yeah.
I get it.
Yeah. Everyone else happy? Okay. So, it looks like I got an A up top and a negative A up top, so those can cancel and leave me with an H up top over an H on some stuff. And that stuff happens to be exactly that conjugate. And then finally the H's cancel, leaving me with 1 over that conjugate.
Wait, what happened to the A plus H minus A on top?
This A plus H minus A, the number one, because everything is being added, there's no multiplication, these parentheses vanish.
Oh, that makes sense.
Okay. Okay. Comments, questions? So we you guys can't see that bottom, can you? Yeah, that's the finish line there. Okay, done. Let's move on from the difference quotients. But before we do that, let's remind ourselves of this. Let's make a quick note just somewhere nearby where you're working. You might call this techniques for difference quotient computations. First, polynomials, things like x squared. So in other words, f of x equals to x squared, or x cubed, or even things like 4x to the fifth, even things that are complicated that might have a constant in front of it. All of these, the techniques you're going to use is what? Do anyone remember what we did the first time? So the first time we did this. So as a quick reminder, if I were to give you like x, we did x to the third. If I give you x to the fourth and ask you, so as an example, you're going to say, okay, I've got to expand a plus h to the fourth minus a to the fourth over h. And then here is where this technique goes. Anybody remember what this technique was? Yes? Pascal's triangle. You expand this thing. You expand that and proceed. We've done that in the note. It's in the notes written up week 1. Look it up if you've forgotten. That's true all for polynomials. We just did today some rational functions. So we did f of x equals to 1 over x. You should ask yourself, is it really going to be any different if I put a 2 up there and maybe even have an x squared down here? No, it's not going to be any different. Same technique is going to apply. The technique here would be, I'm going to write this one Pascal's. This one is going to be common denominator. And let's do one more at the bottom here. We just saw radicals. So in other words, f of x equals to like square root x, or even the cube root of x. The technique is always going to be the same, and it's going to be rationalize. So you've got like a little toolkit for computing these. And what technique you use depends on what problem you're given. Okay. You've had a chance to kind of think about algebra review. I bet my internet's still broken. We'll try it. Oh, I love the security. I love the fact that Chris Greer is telling me that I can't log on right now. So many questions on algebra review, web work. We do meet again on Wednesday. I'll have this sorted out by then, certainly. So when you are at home on Wednesday, zooming into class, not zooming, but into class, feel free to interrupt me and say, hey, I found some time to think about the algebra review. Can you work through number 2? And I'll be like, yeah, great. I'm glad you asked. All right? So that's how I'd like to go through class. Even when you're online, ask me questions from that algebra review. So I'll just show it to you for those who would like to know what I'm talking about. Let's see. These are algebra and limit problems. And all we need is here. So the first one looks like this. So what you should know at this point, and if you don't, you got to ask me super pronto how to find equations of lines through points. We need to understand how to simplify expressions like this. You can see part C. We already were using some of those techniques that you would use in part C, right? You would flip-flop and multiply there. So that's the first page. Logarithm problems, both combining and expanding. So that's it. If you know that, then I'm preaching to the choir, and you're done. But if you don't, that's something that you need to get working on. The solutions are posted already to that sheet, and that looks like this. Then they're on the web. So these, or at least that's not the solutions. The solutions look like this, and they are on the web already. So get your nose to the website and start studying. Yes, ma'am?
We don't turn these in, right?
Correct.
Okay.
But it's like this magical little thing where you don't turn them in, but they turn out to be really important. All right. Cool. So that's the algebra review. Get your, in a typical class, like if we were not collectively suffering through a global pandemic, I would print these out oftentimes and bring them into class, and we would work on them together for a portion of the class. That's what would frequently happens. Okay, let's learn something new today, shall we? Any other questions? Okay. What are we going to learn new today? Let's study a bit of trig. Okay. So first off, let's draw yourself a nice circle. Kind of large, not huge, but kind of large. And think of this thing as the unit circle. So what that means is something very precise. It means that this circle sits on the plane. So we're sort of imagining our entire universe right now is just sitting in the plane R2. It's sitting in the plane. This little dot here corresponds to 0, 0. 0 to the right, 0 up north. All right. Now, this unit circle means the radius of this guy is 1. And if the radius is 1, then I don't recommend drawing this, but if you look immediately to the right, you'll see where that line crosses the circle, there has to be a dot here. And this dot, it only makes sense that dot has coordinates 1, 0. Likewise, if you go completely north, the dot's dead ahead it has coordinates 0, 1. You go over 0 and up 1 to get there. Now, what we're going to do in this trig review is to figure out some kind of standard points on the unit circle, and there's 3. I guess there's 3 in between here that are not really equally spaced. Sometimes we draw them equally spaced, but they're not. But they look something like that, and they're kind of like they're sort of mother points that will generate all the others. Okay, so these points, I'm just going to, instead of like showing you the theory about where they come from, I'm going to show you something to help you remember what coordinates they are. And so basically they involve this kind of thing. So this angle that I'm making from the origin to the 1, 0 point, that's 0 degrees. So this, I'm just going to leave that line there actually and call that 0 degrees. Or that's you think about that as being 0 radians. If I go up 1 notch, we're going to call that 30 degrees, and then up 45 degrees, and then 60, and then finally 90 degrees. In terms of pi, right, remember pi is equal to 180 degrees, and so we can convert 30 degrees to radians by multiplying by what? Pi over 180. You're essentially multiplying by 1. So this is pi over 6. So this first guy is pi over 6, and we're going to leave that. You can just write equals pi over 6. This turns out to be pi over 4. What's 60 degrees? Pi over, exactly, 3. And finally, 90 degrees, pi over 2. That's a good spot to stop initially. Alrighty, the coordinates for those. Little trick. It's pretty easy to remember. It's not it goes like this. Start at the top where you have this sort of space. You should have created some space for these points already, and just start at the very top and count. 1, 2, 3. Move over to the right and go back up. 1, 2, 3. Pretty easy. Now divide everything by 2. And finally, take the square root of all of the numerators. Square root of 1 is 1. Square root of 2, square root 3. Square root of 1 is 1. Square root 2, square root 3. Done. So that's some of the so-called terminal points on the unit circle. Okay, we're getting close to, at this point, this is all geometry. There's no really trigonometry. Trigonometry has to do with ratios, and that's where the functions come in. Okay, so here we go. I'm going to write the word definition here. So sine of theta. What is sine of theta? I'll be pretty darn impressed if someone can tell me in English what is sine of theta, like in general. Like, what does sine even mean?
It's all that trigonometry, like sine, cosine thing.
That's not the definite formal definition, but you're in the right ballpark. What I'm looking to be impressed by is like, SOHCAHTOA. So sine opposite hypotenuse, right?
Yeah.
Opposite over hypotenuse. Okay, fine. It's not where I'm going to start, but just to connect with what you said. So what's the hypotenuse in all these triangles? In each of these triangles, I'm going to draw it here just briefly. This triangle there, what is the length of that hypotenuse? 1, exactly. So 1 has to be the denominator, and the opposite, if you want to think about like whatever that is of this angle, well, it's just this length here, Well, that length here, that's what I was looking for the definition. That was what I was hoping somebody was going to tell me. And it's just the height of that you would be at if you walked theta degrees. So it's just the height. So it would technically, this would be height. But what I'm really looking for in terms of the definition is this. Sine of theta is the height, or specifically the y coordinate of the terminal point corresponding to theta. So if you walk 30 degrees, we always start here at this. We always start here. And if you walk theta degrees, if you walk, say, 30 degrees, so as an example, let's do an example here. So if you walk 30 degrees, how high are you standing?
Like 5.
You got it, 1/2. If you walk 30 degrees along the unit circle, I haven't said that, but that's implicit. I'm walking 30 degrees. How high are you? You're exactly 1/2 unit. Guess what cosine is defined as? X coordinate, bingo. So cosine is the x coordinate corresponding to theta. So as an example, cosine of pi over 3. Find pi over 3. Think about what's the x coordinate of that terminal point, and you also get 1/2. That's it. That's all trig is. That's all sine and cosine are. Yes?
So how do you know that it is 1/2?
Because I know cosine is the x coordinate corresponding to theta. Now this I'm trying to I'm not saying a lot. What does that mean? What does that mean? Well, I am walking along theta radians, so I'm going, oh, stop it. I'm walking along theta radians, and I'm getting to pi over 3. Here I stand. Now, what is my x-coordinate? It's 1/2.
Oh, okay.
Got it. Cool. Anybody else? Comments, questions? Okay. Now, let's talk about tangent. Anyone know anything about tangent? All right, let's do that. Let's do that here on the same page if we can. Let's move this thing up. Say, here's a good spot. And down here, let's write tangent, because it's important to know what the definition of tangent is. Tangent is pretty cool. It's my favorite, I think, of the trig functions. It's just the slope between origin and the terminal point corresponding to theta.
So terminal point is like one of the dots.
Yeah. Terminal points are one of the dots. So I'm going to make them green. Here they are. This x-coordinate should not be green. Okay, so, and slope, it's up to you to remember that. What's the slope from your grade school days? The what over the what? Rise over the run, every day of the week, twice on Sunday. So, with the rise is the y-coordinate. The run is the x-coordinate, so it's just y over x. It's just, or y over x, or, even better, sine over cosine. So, it's pretty amazing that this is the definition of tangent, sine over cosine. And that's kind of a lot to remember. I like to sometimes just remember that it's the slope. So what's the tangent of 45 degrees? Because you go over root 2 over 2 and you go up root 2 over 2. That's it. So just as an exercise, what's tangent of pi over 3? Well, so find the y coordinate of pi over 3 and make that root 3 over 2, and divide that by the x coordinate. Those 2's cancel and you get root 3. That's it. Okay. Cool? Yeah. Sorry. Okay, so that's a little trig review. Let me connect, in the last 7 minutes we have, let me connect a bit of the trig to some of the things we're talking about. Inverse functions, and we're going to soon be talking about limits. So let's do that. You ready? Okay. I would love to turn this off. Okay, good. Okay, so here we go. Okay. Okay. So as a first, first a non-trig example. I'm going. So let C of t be the number of people in the United States with COVID-19. And and while you think about that, I will pause for a moment and say, I'm going to try to find some balance between like doing math with like in the context of like the coronavirus epidemic, and not do too much of that because you're probably all like tired of it all. But I'm also kind of like consumed by it all the time, and math's pretty relevant, so it's impossible not to. So I'm going to try to strike some balance between talk about it some without always talking about it. So here is us talking about it some. Alrighty, that's C of t. It's the number of folks in the U.S. with COVID-19 at time t measured in seconds. Or let's do days. How about that? Okay. I would like someone to tell me in English, what does that symbol mean? C -1t. C -1t. As a hint, it means the inverse function of c. So in English, so that's how you would read that. But how is it defined given what c is?
The number of people who do not have COVID-19.
So not quite. What you're thinking there, I'm thinking maybe is like, I don't know what that negative, you might be thinking of that negative is like 1 over c or something. That negative there, in terms of functions, it always and forever means the inverse function. And here's what that means. Remember, how do you find an inverse function? You swap the x and y, right? And so you don't, instead of solving for x, you're solving for y. So instead of it being about number of people, no, this function is about what? It's about time. So it's at what time did the U.S. have 1,000 people with coronavirus? At what time were there 1 million positive cases? At what time were there 0? So it's almost, so it's like this. It's like, so this is number, this is at what time were there T people with COVID-19. So you see how the independent variable here, so here the independent variable was time, and the dependent variable was people. Down here, that's just reversed. So here, the independent variable, wait. The independent variable is time, yeah. Here, the independent variable is people. And the dependent variable is time. Cool? Promise? No? All right. So that's kind of a neat example to think about. Now, what we want to do is trig. We've got 2 minutes, and we're going to do this. So then, knowing what you know about sine and cosine, tell me what inverse sine of x and inverse cosine of x, and also arc inverse tangent. We often call these arc sine, arc cosine, and arc tangent. Okay, someone from this side of the room. In English, what is arc sine of x? You might have to look up your notes to think about what is sine again, and all you have to do is take those independent variables and dependent variables and swap them. So what does sine eat? Sine eats radians, it eats degrees, and it spits out y coordinates. So what is arc sine going to eat? Y coordinates. So let's just write that out in English. So it eats y coords. What does it spit out? It spits out angles. Right? What is sine of theta? Or sine, what does sine do? Forget the variable. What is sine? Sine says what y coordinate corresponds to a 30-degree angle. Arc sine is going to say what angle corresponds to a y coordinate of, say, 1/2. That's the idea. Okay, we're out of time tonight. Write down your definitions for arc cosine and arc tangent. Confirm with them with a friend or me, and then you will know what the definitions of the inverse trig functions are. Stick around if you have questions, concerns. Otherwise, see you. Technically, I'll see you on Thursday. In person, I'll see you on virtually on Wednesday. Have a good one. Office hours 2 on Tuesday. Good time to find me on my office, on the syllabus under the office hour link. Click on that. It's a virtual classroom just like we have normally. I'll be there. It'll just be a couple of us at most. We can talk math. Do that. Have a good day.
I have a question about your office hours because I have classes during all of yours.
Okay.
So
Send me an email and let's find a time to meet. 3 o'clock will often work. 3 o'clock works sometimes. Tuesday's pretty open too in general. So let's just so we can start by sending start via email and finding out a time that works for us both.
Okay.
We can do it.
yeah, thank you.
Sure. Yep.
What is the Google Classroom code? I don't think I didn't get an email on.
Okay.
Google Classroom?
All you have to do it's not Classroom, it's Google Meet, but I know.
Okay.
So all you got to do is go to the website and then find the link that says Virtual Classroom,
Okay.
or find the link that said Virtual Office. Both of those. The Virtual Classroom goes to the classroom. The Office goes to a separate link, but that's where we hold office hours.
Okay, thank you. I thought that I heard someone earlier say, class
Yeah.
Now that would probably make sense, but
Uh-huh.
I just wasn't certain.
Mhm.
Also, is it like a club fair there?
Yeah.